Hey everybody, hope you're doing well. I want to talk about a problem called the rectilinear motion problem. So this particular problem involves the position, velocity, and acceleration of a particle. The velocity is the first derivative, the acceleration is the second derivative. In these problems, we're only going to consider particles that move in a straight line. When we get particles that move in, say, 2 dimensions or 3 dimensions, there's a complexity that arises that I don't want to get into when I introduce this. That's really a Calc 3 topic. So this file you can find on our Moodle site, and it would be a good idea if you read through it. So you should pause the video now, take a look at this file, and then come back to this when you're done. Okay, so hopefully you read the document. And here's a basic problem that I want to talk about. And I'm going to do some of the problem right now. So I'm going to walk through this with you, and it's really important that you understand what things mean here. This is really a building block for chapter 3. So much of this we have done before. So here's an example. I'm going to have a particle, it's going to be in a straight line, and the position of the particle is going to be given by t cubed minus 6t squared plus 9t. There's a whole bunch of questions that we have to look at here. I'm going to go through some of them, and then I'll have a part 2 of this video, and I'll get through the rest of it after that. So we need to figure out the velocity, which is just the first derivative. I'm going to have Mathematica do some of the calculations for us, and then I'm going to go to a sheet of paper, and I'm going to write down what all these mean. I'm going to draw some pictures of what these mean. We need to figure out the velocity after 2 seconds, after 4 seconds. When is the particle at rest? Well, that's when the velocity is 0, and that's where the solve command is going to become very useful. Moving forwards and moving backwards, that's where the velocity is positive or the velocity is negative. We're again going to use Mathematica to do most of our calculations. We could do this by hand, but we have the tool, so I would like to use it. And then part E, we have to draw a diagram to represent the motion of the particle. That I'm not going to do in Mathematica. Drawing pictures are not the best thing in Mathematica. I'm going to use the document camera for this. And then part F, I'm going to find the total distance traveled by the particle during the first 5 seconds. And that's where I'm going to end this video. I don't want it to be too long. So let's get started. The first thing I need to do is make sure I clear my variables f and t, and I type in my position function. So if I want to figure out the velocity, it's very easy in Mathematica. It's just an f prime of t. Now I'm going to do a shift enter. And of course you can do this by hand. The derivative of t cubed is 3t squared. The derivative of negative 6t squared is negative 12t. Derivative of 9t is 9. That's not a hard part here. What I'm going to do is make sure that I suppress some of these. So the next question, part B, and I will put in a comment, part B. Find the velocity at 2 and 4 seconds. So f of 2 and then f of 4. But I can go back and do 2 and 4 at the same time if I do curly brace. Now, do I want the velocity or do I want the position? So I better be really careful about this. Did I type in velocity here or did I type in position? Well, velocity is a prime. So I wind up getting negative 3 and 9 out of this. Well, what does that mean? Negative 3 is a velocity. That means it's going back. And then 9, that means it's going forward. So somewhere in between moving backwards and moving forwards, the particle had to stop moving. And that's where part C says. So part B gives me, my answer should be for part C, particle at rest, be time between 2 and. So part C, if I put a little comment in here again, I want to solve, whoops, if I can spell solve correctly, where the derivative double equals 0. So that's going to give me t equals 1 and t equals 3. So it actually stops twice in this problem. But does it move forwards, backwards? That's part D. And that's where I'm going to probably write down some stuff, but I'm going to do one little calculation first. And then I'll write it down, and we'll see why I did this calculation. So for part D, if I look at part D, it says, when is the particle moving forwards? That is the positive direction. Well, I have two critical numbers here. I have the number 1, the number 3. T equals 1 and t equals 3. What I want to do, and I'm going to draw the picture first for you, is I am going to draw a first derivative line. This problem starts at 0, ends at 5. If you read a little bit further, part H, it actually tells you it goes from 0 to 5. One of my critical numbers is 1, the other one is 3. What I want to do is figure out if f prime is positive between 0 and 1, whether it's positive or negative between 1 and 3, and between 3 and 5. So what I'm going to do is pick test values. And my test values are going to be 0.5, 2, and 4. 0.5 is between 0 and 1, 2 is between 1 and 3, and 4 is between 3 and 5. So I'm going to try to use both of those numbers, or sorry, all three of those numbers. And I would like to plug them into the first derivative. I'm going to plug in 0.5, 2, and 4. I will evaluate this, and I wind up getting, it's getting a little crowded here. So let me suppress that and suppress this for a little bit, reevaluate it. I wind up getting 3 outputs. I'm looking at output 28 at the moment. 3.75, -3, and 9. So that means between 0 and 1, my velocity is going to be negative. I'll just put a negative sign there. Between 1 and 3, well, my output was negative. Ooh, my bad. 3.75. Raw video, no editing. 3.75 is positive. Just got to read the screen correctly. Between 1 and 3, my velocity is negative. Between 3 and 5, my velocity is positive. So I would like to write down forwards, backwards, and then forwards again. Please include those words in your work. So when I plugged in 0.5, I got a positive answer. When I plugged in 2 into the derivative, this is the derivative that I'm plugging stuff into, I wind up getting a negative answer. When I plug in 4, I wind up getting a positive answer again. So that's what these numbers actually mean down here, this 3.75, this -3, and this -9. Moving forwards, moving backwards, moving forwards again. And that's part D. Part E is draw a diagram to represent the motion of the particle. Well, I have all the information already written down on my paper. Now I just want to draw a nice picture for it. So let's go back to my picture. And I'm just going to tell you that the particle starts there. I don't know where it's actually going to start at the moment. I mean, I can figure that out, and I will figure that out in a moment. In the first second, the particle moves forwards. So it moves forwards for 1 second, but then it goes backward for 2 more seconds. And then again, it changes direction after 3 seconds. So what I would like to do, I want to figure out the actual positions at these very important points. S of 0, S of 1, S of 3, S of 5. Remember, I am calling this function f. So before I do stuff and draw a picture, let's just do a little bit more in terms of figuring out positions. So how do I figure out those positions at those specific points? Well, for part E, I want to figure out the position at various points. 0, 1, 3, and 5. Oops, I forgot a comma in there. 3 and 5. I wind up getting output 0, 4, 0, and 20. I'm going to transfer that to my paper here. 0, 4, 0, and 20. So that means I am going to start at t equals 0 with a position of 0. That's what I would like to write on this first starting place. It moves forward 1 second to t equals 1 with a position of 4. And then I know it turns around, and I'm going to turn it around like this, and it's going to go back to t equals 3. It's still s equals 0 here. I mean, that's what I have over here. And then it turns around yet again, and it goes to t equals 5, s equals 20. So this is my answer for part E. This is a diagram that I'm going to be asking you for. I call it the little snake diagram because it goes back and forth. So I want to answer one more question before I stop this, and then I'll do the next part in a different video. So part E, draw a diagram to represent the motion of the particle. I already did that. Part F, the total distance traveled by the particle. Well, the way I need to do that, I have this trip that I have it in 3 parts. I have a forwards part, a backwards part, and a forwards part again. Forwards, backwards, forwards. Let me label that on here a little bit nicer. Forwards, backwards, forward. So I have 3 parts of the trip. I have part 1, part 2, and then part 3. In part 1, it goes from s equals 0 to s equals 4. 4 minus 0, I'm going to take absolute values because I want to have a distance. So in this part of the trip, I travel a total of 4 units. This part of the trip, it ends at distance, or ends at position 0, but starts at position 4, and I still get a 4. Part 3 of the trip, it ends at position 20, but starts at position 0, and that also has a total distance of 20. So total distance here, four plus 4 plus 20. So I did a lot of my calculations by doing all this. Now I just had to do some simple arithmetic. If this didn't turn out to be 0, or this didn't turn out to be 0, then I'm going to wind up having slightly different numbers. So my final answer is 20. And that's going to end this video. I hope that this was helpful. See you later. Bye.